Hello, I'm David Noel. Welcome to episode 07 of Cmbr. The topic today is Cmbr, Cosmic Microwave Background Radiation. Cmbr is electromagnetic radiation which comes to us from all over the sky. This radiation is in a band with much longer wavelengths than visible light. This band lies at the junction of microwaves, which are the shortest radio waves, and far infrared. In earlier years, we didn't have equipment which could detect or generate radiation of these wavelengths. This didn't happen until the development of radar in the 1940s. In 1965, two American astrophysicists, Penzias and Wilson, built equipment to detect sources of microwave radio emissions from the Milky Way. Their equipment was a huge piece of apparatus called a horn antenna. With the horn antenna, Penzias and Wilson were able to observe many microwave emissions from points of the sky, but wherever they pointed their instrument, there was also background noise. If this microwave noise was in the visible spectrum, it would be as if the whole sky was brightly lit, whenever you looked. Penzias and Wilson realized that the Earth was receiving this background radiation from the whole celestial sphere. This was great work for which they received a Nobel Prize. Unfortunately, when they published their work in a journal, one of their colleagues had an idea for the origin of Cmbr, and this was published in the same journal. Once this idea for the origin of Cmbr was published, it was generally accepted and never looked at critically. But the idea was totally mistaken. Here we will show the true origin of Cmbr. For this, we need to look more closely at the real properties of Cmbr. Out in deep space, the biggest portion of electromagnetic radiation received by a body is Cmbr. Here's a pie chart of how this received radiation is made up. This chart shows how more than 70% of the radiation coursing through free space in our region is made up of Cmbr. And this is in energy terms. If the chart showed the proportion in terms of photons, Cmbr would make up over 99% of them. It would be ludicrous to suppose that energy released more than 13 billion years ago could still be a major item in the universe. It would all have been absorbed billions of years ago. So that's the first reason why Cmbr could not be radiation left over from the past. To still function as a major source, it must be produced by mechanisms still active today. We saw in episode 01 that the universe is not expanding. Even if it was, it could not have stretched light from the Big Bang to the extent suggested. It's always assumed that the Big Bang produced visible light. For light to be stretched from visible wavelengths out to microwave wavelengths, it would have to be moved down 4 octaves, far too much to occur in 13.7 billion years. And if this happened with Big Bang light, why did it not happen with other light sources, such as the stars we see with light over 13 billion years old? And of course, we know from episode 02 that the Big Bang never happened. We need to look elsewhere for the origin of Cmbr. We know that Cmbr comes from everywhere in the sky. Here is a picture of how it's usually represented. This picture is hard to understand without some explanation. The first thing is that the picture covers the whole sky, wrapped around so the leftmost point is actually the same as the rightmost point. It's produced on what's called a Mollweide projection. This is easiest to appreciate by comparing it with a Mollweide projection of the Earth. On the Mollweide Earth, just as in the Cmbr picture, the whole of the surface of the globe is represented. For the Earth, its entire surface is represented in the oval. For the Cmbr picture, the whole of the celestial sphere is covered. On the Earth picture, the long axis of the oval is the Earth's equator. For the Cmbr image, the long axis is the plane of our Milky Way. What the different colours represent is slight variations in the wavelengths of the Cmbr received from different points. In many cases, this is because the temperatures of the bodies emitting the Cmbr themselves vary slightly. The redder areas represent emitting bodies hotter than the average. Blue-black is from cooler bodies. We'll see later on that this average temperature is very low, only about 2.7 K, that is 2.7 degrees above absolute zero, the coldest that real objects can get. For comparison, room temperature, say 17 degrees C, is equivalent to 300 K. Absolute zero is minus 273.1 degrees C. We'll go on now to see why Cmbr has the wavelengths it does. In the early 1900s, the brilliant German physicists Max Planck and Wilhelm Wien discovered the laws governing how bodies emit radiation according to their temperatures. This is what's called Blackbody Radiation. It's called Blackbody Radiation because it applies to a theoretical object which it absorbs 100% of all radiation it receives. The laws discovered by Planck and Wien are surprisingly precise. They show that the radiation emitted by an object depends directly on its surface temperature. The radiation is not all at one temperature, but has a characteristic variation of energy with wavelength, giving a humped shape. The peak energy output is at a wavelength given by Wien's law. In the graphic, the green peak is for an object with a surface temperature of 5,500 degrees. This could be a yellow star. For a cooler object, the total energy falls and has its peak at a longer wavelength. Another important point is that the energy emitted by a radiating surface is proportional to its surface area. Let's look at how these V curves turn out for everyday objects. In the graphic, the top left curve is for our Sun, which has a surface temperature of around 6,000 degrees. You can see that its light output has a peak at a wavelength of about 500 nm, which is blue light. You might also notice that the Sun puts out some radiation with a wavelength shorter than 400 nm. This is ultraviolet light. There is also quite a lot of radiation at over 700 nm. This is infrared light. Next, look at the middle top curve. This is for a red-hot object, such as an iron bar heated in a furnace. With a temperature of 1800 degrees, its radiation is almost all in the infrared. Just a little, between 500 and 700, is visible red light. On the top right, with a temperature of about 300 K, or about 17 degrees C, is the Earth's surface. All of its emission is in the infrared. On the bottom right, we have the Wien curve for Cmbr, which is for objects at 2.7 K. The peak radiation wavelength is close to 1 millimetre. So, where in the universe will we find objects with a temperature of 2.7 K? The answer is out in the Oort cloud, the vast expanse surrounding our solar system. Here is a picture representing the Oort cloud. The top insert shows the solar system. To describe distances in this field, we often use, as a unit of distance, the AU, or astronomical unit. 1 AU is the distance from the Sun to the Earth. Moving out from the Sun, the most distant planet is Neptune, which is at about 30 AU. The edge of the solar system itself is at about 100 AU. Beyond that is the Oort cloud, essentially all sorts of interstellar material called the Oort soup. Within the Oort soup there are no sharp boundaries, but for our purposes we can suppose that our Oort cloud extends out to 100,000 AU, that is about 2 light years, almost halfway to the nearest star. Within our Oort cloud there is quite a lot of material. This includes giant planets, moons, asteroids, and much more. Everything under the minimum mass of a star. All the objects in our Oort cloud have a mass adding up to 9 times the mass of our solar system, but it is spread very sparsely over a volume 1 billion times the size of our solar system. Almost everything in the Oort cloud is very cold, under 3 K, because it is a long way from any heat sources like stars. It's clearly the source of our Cmbr. As to the huge volume of Cmbr in our universe, one reason is that most of our Oort soup bodies are relatively small. The aggregate surface area of a body increases as the square of its radius. So the total emission from the combined surface areas of these small bodies is very high. The Oort soup bodies are also the source of what's called dark matter. Dark matter is a topic which is dealt with in episode 08. Following is a link to a referenced article on the web which gives more detail and links on the current topic. And finally, some links to other sources available to you, both episodes on our YouTube channel and a website including articles which quote established and referenced data. Have a look. Thanks for watching. I hope these SMB episodes are useful for you. Till next time then, goodbye from David Noel.